All right, great, let's go. Howdy, I'm Cory. I work at Apple on the Swift Neo team. This is essentially a follow-on talk from a session that my colleague Johannes, who is also here, did at DotSwift in Paris last year. The rough summary of this is that building Swift Neo and continuing to build Swift Neo has taught us an enormous amount about writing high-performance Swift code. While it's really important to have high-performance code on the client for battery life and CPU usage purposes, failing to have high-performance code in high-scale server applications is very, very obvious. You tend to notice it very, very quickly. It leads to catastrophic failures and angry users. So as a result, we've learned an enormous amount of lessons about how to work around some of the most substantial and easy to resolve performance problems in Swift. I mention all of this to say, to begin with, I'm building on top of some work we've done and laid out before at the .Swift conference in 2019 about value types. I'm going to share some lessons learned, some tips and tricks. This is not a hard prerequisite for you to have seen this other session. I'm going to try to recover some basic territory really quick. But if you're interested in more high-performance Swift content, you can go find this talk up on YouTube. There's a bunch of content over there. It's also super interesting, super valuable. All right. So before we go any further, let's talk about value types. What is a value type? The easy way to understand what a value type is to talk about specific examples of value types. Integers are the easiest one, so let's go there first. This program creates an integer, calls it x, sets it to 1, creates a new variable y, sets that to the value of variable x, modifies x, prints the result. It's a great program. Submit this for your master's thesis. It'd be perfect. In this program, the modification of variable x that we do in line 3 affects only the value stored in the variable x, not the one stored in the variable y. And I guarantee most of the room has heard the tone in my voice there and thought that I was being extremely condescending, because this is extremely natural to the vast majority of people who do programming, especially anyone with really even moderate professional experience. This is how we expect integers in programming languages to work. Almost any programming language you can think of has integers that work in exactly this way. But this idea is not actually trivial from a theoretical perspective. This idea that modifying one value will not affect values in other variables is actually an idea with a name, and that name is value semantics. A type with value semantics, like integer has, is a value type. Restating that, a value type is any type in a program where we expect each variable to store a value of that type that is independent of every other value of that type. Mutations are locable only to that variable. Every other value in the program stays the same. All right, fine. So lots of languages have got value types. Most of them restrict value semantics to simple types like integers. Swift is pretty unique in this case because it makes value types substantially more pervasive throughout the language. In Swift, for example, quite a few fairly complex types actually have value semantics. For example, Swift's array type, or in the world of really very complex types, Swift's dictionary type also have value semantics. What this means is you can write programs like this one, which would surprise almost anyone who has written, for example, Python. If you write the program like this for Python, you do not get this output. This is simply not how Python programs work. But for Swift programmers, this is one of the things that we very rapidly get quite used to. We create the array 1, assign it to a new value, mutate the original, and we have 2 separate copies now. And this is super nice, because this allows what is frequently called local reasoning. Essentially, you can look at a relatively constrained part of the program and understand what is going to happen to any value type in it, because the changes are local to that value. They aren't weirdly reflected elsewhere in the program, what is frequently referred to as spooky action at a distance. But there is a question here, right? How does array do this? It's a neat trick, right? When we think about value semantics for integers, it's pretty easy to understand how this might work, right? You write the var x equals 1 and you create a little box somewhere in memory, let's not worry about where. It's the size of an integer, and you stuff a 1 in it. When we do the next line, we create a new box for y, and we copy the value x for x out of the box for x into the box for y. Now they both have 1 in them. That's great. And then we run the next line, line 3, magical line 3. And this changes the value in the box for x, but doesn't touch the box for y. Because each box is independent, the value has changed only for the variable x. And this makes perfect sense. Why would variable x know anything about the box for y? It has nothing to do with x. It'd be very strange every time we wrote a little program like this for variable y to keep track of every other x that it came from. That would be very strange. So this feels pretty straightforward. But arrays are not like integers. An important thing about arrays is that they are variable-sized data structures. The mere fact that you are holding an array doesn't tell you anything about how big it is. How big it is depending on what it's storing. Data structures like these, as a result, tend to have to be allocated on the heap, and they have, largely speaking, an indeterminate size. This means if you want to create a little box that's always the same size, the thing that has to go in that box is a pointer to the actual storage. Okay, fine, let's assume that that's the underlying data structure for an array, underlying representation. So when we create our array x, we allocate some space on the heap, put a 1 in there, then we create a little box, and we point to that space on the heap. This is, again, mostly fine, mostly intuitive. So the next line works the same as the integer case. We create a new box for y, we copy the value in the box. Pointer value is the same, points to the same memory. This is great. This is super efficient. You can imagine if the array was 100 million elements long, it would have been pretty unpleasant to allocate space for it, copy all the points over, and then point to the new thing. That would be pretty bad. So we have this super efficient strategy which allows us to just alias the underlying memory. But we now have magical line 3, where we want to mutate one of our values. What do we do now? We have to remember the rules. The rules are that each value appears to be independent. Now, we know that they're not, but we have to behave as though they are. So what that means is we need to change what x is pointing to without changing what y is pointing to. And when I put it like that, it should begin to seem somewhat straightforward how you might achieve this. To get an idea, though, we're going to rearrange the view. We'll split x and y out. We have 2 values pointing to the same memory. We want to write to x in such a way that x and y have different values. What we do is called copy on write. We allocate a new box, we copy the old data into that new box, and then we mutate the new box. Finally, we rewrite the box for x to point at our new heap allocated memory. All the other values in the program, which we don't know anything about, they're unchanged. They still point at the old heap memory. They still see their old values. The new one, the only one we changed, gets its special heap allocation occurring, and then the modification is there and there alone. This is a super neat trick. This lets you get value semantics for variable length data structures. In fact, if you go and look at Johannes's talk, which includes material about writing your own copy on write value types, you can get value semantics for any type if you are willing to put in the work to do it. There is no special standard library magic here. All Swift programmers can write arbitrary value types this way. You can implement it in your own applications and frameworks. I'm not going to go into how, it's just not the focus of this talk, but it's super worth investigating. It'll give you a bunch of appreciation for what Swift does and how the standard library works. All of this, what I just spent 8 minutes telling you about, is not the point of this talk. I'm not talking about that anymore. We've got this really great way to get these powerful value semantics in our programs, but it is reasonable to ask how this might affect high-performance code. In general, copy on write is great for high-performance code. It provides these powerful optimizations to avoid copying memory around. It makes our code really clear and semantic. It helps us understand how things will work, which makes us write more efficient programs that are less likely to run into weird data ordering problems. But in some specific cases, this can lead to performance problems in your code. The reason for this is that copy on write is super great when you need it. And when I say when you need it, what I mean is that the way you wrote your program, it is only correct if the cow occurs. However, in some cases, you will write programs that don't actually need to perform this copy. In a completely perfect world, you could understand that there will only ever be one instance of this data. It doesn't need to be copied around. We can just mutate only the one underlying instance. It can happen, however, that the way you wrote your code means that the Swift compiler cannot see this. And as a result, it will issue a cow. It will allocate new memory, copy the value over there, and frequently then end up several operations later freeing the old data store that you no longer need. This cow is what I'm going to refer to for the rest of this talk as an unnecessary cow, and they can really hurt performance. There were unnecessary cow jokes in this talk, and I've taken them out. I thought they were a distraction. We can laugh now. All right, so the reason that unnecessary cows can be very expensive is that the cost of this unnecessary copy is linear in the elements in the collection. So when you've got that little one element array, it mostly doesn't matter. But what it means is whatever the complexity factor of your algorithm was before this unnecessary cow gets an extra multiplicative linear factor on whatever the section of the algorithm is that is causing the cow. This is always a nasty slowdown. There is never a point where adding a multiplicative linear factor is not going to be noticed. But when your algorithm is already operating on the collection that you are cowing, your algorithm has gone from being linear cost to quadratic cost. And that is the absolute worst thing that can subtly happen to your program. There is a wonderful blog on the internet called Accidentally Quadratic. I strongly recommend reading it because it is the single greatest performance cost and, for server applications, denial of service vector that you can possibly put into your code. To go into this in a bit more detail, I'm going to do the most dangerous thing a presenter can do, which is I'm going to do a live demo on beta software. So, got to extend these displays, bring you back to my world. We're going to open up Xcode. So, I've got some Xcode here. This is a Swift server application, that rare beast. And it's a Swift server application that runs a web service. Now, I would like to apologize to the designers in the room. This is very beta. I haven't run it past the designers yet. This is what I would politely refer to as an engineering UI. But the purpose of this, roughly, is to organize lunches, because, as we know, organizing lunches, very important. Enormous amounts of engineering resource need to be devoted to doing that. The way this would work is you would set it up in your place of work, business, place of leisure, whatever else, and you would distribute the website to everyone, and then you'd say, look, we're going to have a meal. We're going to have what meal? Lunch. Okay, let's create this meal. Who's ordering things? Oh, Tom, what's he having? Tacos. Great. All right. Eleanor, what's she having? Anyone got food beginning with E? Eggs. That was my bad. I blanked on that one. So we go. It's a great UI. We'll put pretty things later. We'll rewrite it with Swift UI Web. It'll be wonderful. But I've given this to a couple of beta users, and they've told me that they've encountered some performance problems with this site, which I refuse to believe because I am a genius and my code is perfect. But I'm polite to people when they file bugs. I would like to test it. So I've written up a quick script that's just going to exert some load on this server. It's sitting in here. You can see I've got this little run load script right here. So just to test, I'm going to run a bunch of load. And what this load script's going to do is, in a loop, it's going to create a meal and then set a bunch of food orders into that meal. And it's going to double the number of food orders it does every time. For the sake of speed here, I'm going to start at quite a large number. So it's going to raise questions about how my colleague found this bug, but we're just going to put 1,000 orders in. So we're doubling the number of orders here every time. What I would expect to see in a well-formed program is that this should take roughly twice as long for twice as many orders. This seems natural, and doing twice as much work, twice as much time seems bad. But the attentive of you in the audience will notice that 5.1 is not twice 1.9. And in fact, we're beginning to have to wait around quite a long time. I'm having to vamp to fill time. Got to say nice things about Bath. It's a very pretty city. Lots of things to like here. I'm worried, is what I'm saying. This is making me nervous, right? So this is pretty bad. And in fact, if my demo was more complex and I wanted to pull up numbers and put all of these things into a chart, you would see that perfect quadratic curve that you are used to seeing from your textbooks for these numbers. We're sitting here now, 32,000, still not done. I still can't proceed with this talk, but waiting for this to happen. This is really the worst case scenario for an application. This is exactly why quadratic programs are bad, because substantially more than 30 seconds have passed now, and we are still sitting here waiting. I can tell you this will eventually complete. I can't tell you when. This is longer than most. So I might actually intervene and kill it now, rather than, there we go, cool. 60 seconds nearly. That's pretty bad. So my colleague's right, I have a problem. And There are many ways that I could have introduced this problem. The most common one, and I need to stress before you go into worrying about the unnecessary copy on writes, the first thing to do is to evaluate the algorithms you wrote into your application. Because, speaking as a programmer with substantial experience, usually the bug is my fault. More often than not, I got it wrong because my code is the thing that's new. The other code in my program has been there a while. It's more likely to be right than the code I just wrote. But hypothetically, let's imagine that we have checked all of these things and we know there are no quadratic loops there. I believe everything in this program is linear. How would I go about trying to track this down? The purpose of this talk here is to give you a little bit of tooling just to work out how to find these unnecessary copy on write operations so that you can track them down and remove them. I should stress, you probably want to remove them even if they are not actually causing quadratic loops in your program. The reason is, work you don't need to do is best not done. It is the single biggest truth of performance optimization. If you can avoid doing it, don't do it. As it turns out, it's pretty easy to track them down. I'm going to show you now how we do it. The way we do it is we go back to Xcode and we break out everyone's favorite Xcode tool, instruments. Is everyone here familiar with instruments? I've got a lot of nodding heads. Let me invert the question. Is anyone here not familiar with instruments? Got a couple of hands. All right, there are some excellent WWDC sessions about instruments that I cannot remember off the top of my head. Come track me down later and I'll give you some citations for them. But we're going to come over here. This is the rough start of the instruments UI. There are a lot of great tools here. I strongly recommend investigating all of them. But we're going to look at the allocations tool today. So I'm going to select that. We've got this horrifying empty box. We don't really know what it's for. But I'm going to hit this record button. Some things are going to happen. And I'm going to go back here and I'm going to run some load. And I have a special flag here that will just run only a medium amount of load. So I'm going to just do one iteration of 8,000 orders. Now, the first thing you'll have noticed here is that this slows down a little bit. Because we have to do a bunch of recording and metrics taking, we don't necessarily immediately take the same amount of time. Okay, we've run instruments. This is the output of instruments, and to many of you who've never run this tool, it's going to look bizarre and weird. There are many pieces of information here, but I want to focus on the allocation summary down in the bottom of the screen. This shows all of the allocations in your program. I'm going to propose that you change the allocation lifespan to all allocations. In this specific test, it's not relevant, but in general, this will help if the thing you are copy on writing is transient and it doesn't exist in your program when you stopped the recording. This can happen. It's an annoying way to miss this kind of thing. It's worth remembering to flick that over. At this point, we get this very detailed view of all the things that were allocated in our program, how much memory they take up, and how many allocations we did. The thing I'm immediately going to look at is which things did we allocate approximately 8,000 times, and which things did we allocate approximately 8,000 times that we threw almost all of them away or that took up a bunch of memory. If we look here, we can see that over the course of that run, we allocated 2.3 gigabytes of memory, which seems high, and 2.13 of them came from this allocation right here. So that seems like a good place to start. What is this? This is contiguous array storage. Contiguous array storage should immediately set off alarm bells in your mind when you see it. Contiguous array storage is the name of the class that ultimately holds the array allocated memory. Okay, fine. Can we track this down? If you hit this little arrow, you'll see every place we did the allocation. And I'm just going to scroll down to roughly the middle of it, click here, and then over on the right-hand side, and I appreciate this is small, see if I can trust that to not get bigger. Down here, you're just going to have to trust me, you can see the call stack for this particular allocation. And here is the function call that ultimately ends up in allocating this. It's array buffer protocol force create unique mutable buffer impl. Now, leaving aside the elegance of that name, this is one of many functions that you'll begin to see when you start looking at copy on write value types that includes the name unique. And whenever it includes the name unique, you should begin to get a little worried, because this is almost always something that was done in order to deal with the fact that we have multiple references to one backing storage. This is the copy on write story. If you look at this stack, you can kind of come to the conclusion that probably this is a copy on write operation. And I did 8,000 of them. That's once per meal in the food order, and that is probably an indication that I'm looping over a copy on write operation. Conveniently, this call stack includes my own code. So I can actually go and find roughly the method which is doing this extra allocation. So let's hop back real fast. Turns out I'm already on the right file. That was lucky. Definitely not preparation. Now, this is a hand-rolled custom web framework, which I highly recommend no one use. But down here is the place where we handle posts to this form, so creating new meals. And what we do is we grab a UUID, we look up a meal in this dictionary, and then here we call a function. Now, I happen to know that this function is mutating on this object, this meal object, and we assign it back. If we dump into here and hop over to the implementation, it's a lot of indirection, but ultimately what we end up doing is calling self.orders.append, and orders is an array. This fundamentally is the array that we are copying. What we're doing is pulling an object out of a dictionary, mutating it, and assigning it back. So what's the problem here? Well, the problem is when we pull this object out of the dictionary still has a copy of it. If we went and looked at the dictionary again, that element would still be there. And it's a value. So when I mutate this local one here, this is a separate element. We must copy on write in order to preserve the integrity of the one in the dictionary. There's nothing inherently wrong with this. But in this program, where I know that the very next thing I'm going to do is write straight back into that dictionary, that is a completely wasteful operation. There is no need for this transient copy here, because the dictionary should be mutated synchronously. OK, fine. That's the problem. What's the solution? Well, the great story here is there are many solutions, and I want to just show you a few of them. So let's comment out this fatally flawed chunk of code and go here instead. So option one is the simplest one. Option one is take it out of the dictionary. There's no need for the value to be in the dictionary here. I'm doing a temporary mutation, so we can pull the value out instead, mutate it, and then put it back. This is fine. This works reasonably well. It is almost always the correct thing to do in an asynchronous context, or it's frequently the correct thing to do in an asynchronous context when you don't know how long this mutation will take to occur. It's a pretty reasonable option, but it's often not the best one. Another option, wow, that was fine. Another option, if you are so inclined, is to use a method called tombstoning. Tombstoning essentially means into the value slot that previously held our value, we're going to put something that is an indication that we've taken it out, some null value. I've defined a null value here, this .tombstone. That's the thing we're going to put in. Tombstoning works in any case where you can define a null value. Optionals are great for this. But in cases where you cannot define a null value, tombstoning doesn't work. In particular, if you have a dictionary of, for example, something to integer. Probably integer doesn't have a good tombstone value for you. Almost any integer in the program is likely to be valid. But it's an approach. Approach 3, which is the best one when it works, but is not always available to you, is to use what are known as generalized accessors. This is some work that was being done as part of Swift 5 that defines new ways to modify data on value types. I'm not going to go into this too much. They're currently available to you only as underscored accessors in your various properties. For more information on this, come see me after. I'm happy to point you at various resources about it, show you how they work, explain them to you. They almost certainly will at some stage proceed through Swift evolution, but they're not there yet. What matters for our purpose here, however, is that array and dictionary both support them. What this means is you can convince Swift that the modification is happening in one go. Essentially, I've moved all of the code here into one line using optional chaining in order to modify the object. This essentially tells Swift nothing can happen in the logical execution of this code between the retrieval of my object, the modification of my object, and putting it back. So let me operate on the underlying value rather than creating this transient copy. If you want to rely on this, I should stress you really must test before and after to verify that your copy on write went away, because it is possible to defeat this in the optimizer. I should also stress you should only run these benchmarks in release mode. In debug mode, there will be copies everywhere, and this is not meaningful in any way. We're going to leave the generalized accessor result in, and I'm going to rerun this load. I shouldn't actually run it in instruments. That will just make my life harder than it needs to be. Goodbye, instruments. Let's run it in normal release mode instead. So we're going to hop back. Remember, this was our pattern from earlier with this strictly quadratic loop. Let's hop back and run the load again. Oh, well, this already looks a lot better. Notably, not only is this running substantially faster for the large cases, it is also running a lot faster for the small cases. The performance of this program has simply improved. Allocating memory, doing copies when you don't need to, it slows you down always, even when the performance is not quadratic. But my problem is gone. This is roughly doubling every time I double the load. This is what I wanted to see. All right, let's return back to this session. I'm going to swap the displays again. Launch iTunes for some reason. You're never too big for a Dell, that's all I'm saying. That's a joke that will have flown over most people's heads. All right, great. So here's the summary of this with the live demo. The first summary is copy on write's great. I should stress, I've just talked about some of the ways it can hurt you, but in general, copy on write's excellent. It is excellent for making your program understandable. It is excellent for making your program fast. It is occasionally tricky and troublesome, but there are great tools for tracking down when it gets troublesome for you. The lesson here is that accidental multiple reference is how you lead to these unexpected copy on writes, when you leave a value somewhere that you didn't expect to see it. This is not something that happens because you don't understand your program properly. It is something that happens just as a natural outgrowth of programmers working. If you want to see proof of this, again, come talk to me afterwards and I'll show you the many times I personally got this wrong in SwiftNeo and how I fixed them. Some of them are interesting, some of them are subtle, some of them are just silly. Unexpected cows lead to performance hotspots, which profiling can help you find. Repeated unexpected cows lead to quadratic performance, which makes your customers sad, and Instruments is your best friend for auditing them. As a result, you can get rid of all of your unexpected cows exactly this way. Great, I hope that's been helpful. Please find me afterwards if you're interested in chatting about this more. Thank you very much for your time and attention.